Hello and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistors, a physics perspective. This is lecture number 51 and the topic of the lecture is CFET advancement and industry adoption of CFET. So CFET, as we have discussed in our previous lecture series, is basically defined as the complementary FET. And the general scheme of things as far as devices are concerned in the domain of VLSI is better the control of the channel by the gate and having more influence on the electrostatics by the gate, better the device will be. And therefore, with passing period in time domain, there has been a constructive effort of one, reducing the channel length, but then also a very concentrated effort has also been spent in order to see that that the gate has got a better control over the channel as compared to anything else. Moreover, the three important pillars or sort of figure of merit which people face is power, performance and area, right? So what we will be looking in this lecture series on this, especially in this lecture, is that within the same area as a bulk MOSFET or a FinFET, can we actually increase the functionality and have both NMOS and PMOS uh, being fabricated within the same area as it is of the FinFETs. So with this, let's start the discussion. So we will look at CFET advancement and industry adoption. The outline of this series will be to give you the challenges and how to optimize CFET. We will also discuss about novel sort of hybrid channel CFETs, and then we'll look at the synthesis flow for a standard cell for the CFETs, right? And since we would expect to see that by 2032 or 31, we would have CFETs as one of the mainstay of technologies, just like FinFET currently is. So we as instructors thought of putting it in front of you to understand the value of CFET. Now, the roadmap which is there, which is generally given by ITRS or IRDS, states that if you want to move to a technology which is basically around 1 nanometer node, 1 nanometer primarily means a 10 angstrom node, then complementary FETs possibly one of the major sort of candidate which can allow you to move to 10 angstrom node per se, right? Without, so there will be issues related to reliability and performance, but the whole idea is not to let the performance go down, and all second order effects can be eliminated in a CFET. Now, what we are looking is that obviously gate all around technology is critical if you want to do a continuous scaling, downward scaling of the transistor. However, one important point you should keep in mind is that the voltage, that is the applied voltage VDD, needs to be also scaled down. If you are actually going for a constant electric field scaling, then you need to also reduce the value of VDD in the similar fashion as L is being reduced, so that the electric field remains constant across the scale. Why can't you go on increasing the electric field is that as the electric field goes on increasing, you will have a problem of maybe dielectric breakdown, you will have a problem of hot carrier effects, which I discussed in the previous lecture series. So these problem statements will be add on to it. So therefore, we need to do that. But the problem with CFET, or for that matter any post FinFET devices, is that as you scale down your VDD, the amount of time taken for the current to move to a high value is very, very large. So since your VDD is small, your current is small. Since your current is small, you actually spend more time in charging or discharging the capacitor which is connected to the inverter, and therefore the loss is basically the frequency of operation. So there's always a sort of a I should say a complementary sort of mechanism in terms of performance when you take CFET into considerations. Now, how is CFET different from anything else? That is written in the third statement here, that in this case the NMOS and PMOS devices are stacked over each other, and therefore further maximization of effective channel width is done within the same silicon sort of real estate. So, earlier let us suppose you are able to make the NMOS in this much area, right? Suppose, let us suppose, and then you try to make PMOS, then you have to make a PMOS here, or and there was a guard ring here. Now, what you are doing is in the same area A, by stacking one over the other rather than parallelly sitting with respect to each other. So, this is PMOS, right, and this is NMOS. So, you are basically stacking one over the other. So, within the same area you are able to generate an inverter for all practical purposes. This is the main architecture of a CFET. We will come to the schematic of CFET, and this is where you see the schematic here. On the left hand side, you see the nanosheet FET. So, we have already discussed this nanosheet FET, that you apply a voltage VDD, you ground VSS, you can even ground it down. So, this can be grounded, and then you apply, this is the gate, A to be the gate. So, this pink colored is basically the gate, right. This gate surrounds my both this channel and this channel. However, what we are trying to do is we are trying to develop a CFET here. What is happening in a CFET? That this PMOS, let us suppose, is stacked over this NMOS. You get the point? So, the PMOS and NMOS are stacked over each other. You will ask me, where is the source and drain? Well, the source and drain are away from the away from the your laptop screens or desktop screens. So, one is away from the desktop screen, another is inside the desktop screen, which you see. This, so you see, if you look at this spacing, this one and this one, it's almost half, which means that your CFETs will utilize half the silicon real estate as compared to a nanosheet FET. And therefore, it is a very promising device for N2 logic technology and beyond. N2 means node 2 nanometer logic technology and beyond, lowering it down. And basically, therefore, since you are stacking NMOS and PMOS, you are actually minimizing the CMOS device footprint, right. That is an important point, that there is a minimization of CMOS device footprint. Let us look at some of the problem statements, even we will go to that later on in much more detailed manner, but let us look at here itself and we will understand what the problem statement is. You see, in the CFET, your NMOS and PMOS, since they are stacked over each other, you need to maintain a certain distance between them, so that the operation of one does not influence the operation of the other, right. What we are limited by is the height of the stack. The stack height cannot go beyond a particular limit, because that is a physical instability will come into picture, which is not available in nanosheets. In nanosheets, you can actually grow in a horizontal direction, right, and you can actually make the sheet stack go higher and higher by making it 3 sheet, 5 sheet and 7 sheet and so on and so forth. In CFET you can do that, but then you end up having stability issues and mechanical stability issues for complementary effects. So, this is a stacked device which I was talking to, right, and this is known as the stacked NMOS PMOS architecture. Now, typically if you take a CFET, you have approximately 2 times higher density compared to a CMOS architecture. If you take a standalone CMOS architecture, right, and you maintain the same gate pitch between two gate metals. How do I define gate pitch? Is something like this, that if I have gate metal and I have gate metal here, then we define the gate pitch to be half from here till half from here. So, this is known as gate pitch, right. We have gate pitch. Now, if you maintain the same gate pitch as an CMOS architecture, then typically the density will be approximately 2 times higher. One issue therefore related to this is that since you are stacking it, the interconnects which will be flowing, vertical interconnects, there will be local vertical interconnects which will connect the upper NMOS with the lower NMOS. These will also undergo scaling, and their design rule checks will be quite different from a conventional horizontal rule checking for the of the electrodes. Now, if you look at the first figure on the left hand side of your screen, right, if you plot area versus the process complexity, then what you get is that if you look at the third device, you see CFET here, so you are able to reduce the dimensions, you are able to reduce the silicon area, but at the cost of higher or even stricter process complexity, because as you can see, as compared to the FinFETs and NSFET, CFETs will have a larger complexity in terms of growth of devices, and typically the density scaling is from 1.5 to 2 times with the same gate pitch. If you look at the second diagram, which is termed as A, then you will see that I have the source drain structure here, source drain, and there is a device here. This is the device. Similarly, I have a source, which is a p-type source, p-type drain, and I have a server here, or I have a metal here, and this is my gate. So, if you apply now a gate voltage, one of the GAA device will turn on, and as a result there will be flow of current. What happens in the third case? So, you can actually then flip it over. So, how can you flip it over? So, these are two NMOS PMOS. So, you basically flip it over like this, right? You can actually flip that. That's what this this arrowhead tells me, that I can do a flipping of one over the other, so that your silicon area is not compromised in any sense. Now, easier said than done, because the right hand side figure, which is part B, is where the integration of NMOS and PMOS is shown for a CFET. Now, there are metal 1 via, right, there is a metal 1 which actually gives a gate voltage for the inversion channel, and we have vias running in the horizontal direction, which connects the various power supply sources which has to be given to CFET. This one is the top contact here. It can be a metal contact, or it can be also a poly contact, right? Poly contact. Then you have this green colored here is your NMOS, and then you have PMOS in the bottom contact. So my NMOS is separated from the metal and via by a top contact, and it is separated from bottom contact by this thing, by applying a proper material there, right, which is, and when you put that proper material, you are insulating effectively the total channel width. This is the bottom contact which you see. This is the bottom contact. This is the bottom contact which you see, and this is connected to PMOS, NMOS here, PMOS, and this is connected to NMOS here, right. And therefore, as you can see, even without doing any too much amount of physics behind it, we have increased the complexity of the device at the cost of the area. So, the complexity of the device is increased by 3 to 4 times, and the area has actually reduced by a factor of 1.5 to 2 times, and that is where we get the advantage of having a CFET in this case. Now, there are two ways in which CFET actually are implemented in a system. One is a monolithic, another is sequential. These two are very important sort of fabrication step which one needs to follow while designing this CFET, and one is sequential and one other is monolithic. Now, in the monolithic flow, the CFETs are fabricated on the wafer, right, through a continuously processed flow, which is something like this. So, you add one layer and then you go on adding another, you go on adding epitaxially, you go on adding, and as you go on adding, what happens is that in the monolithic flow, you go on adding sequentially one after the other, right. The sequential flow, the bottom device is fabricated first, this bottom device is fabricated first, right, and then a second wafer is flipped and attached to the first wafer, and the top wafer is fabricated over the below wafer, and you do a proper alignment of the top wafer with the bottom wafer, so that proper alignment is done, and then you do the metallization scheme. In order to ensure that this device is working properly, you also put up a bonding dielectric between the two, so that there is no leakage path available between the two sequential and the monolithic case. Okay. Now, let us take up the monolithic and sequential comparison, because we need to, at some point of time, need to take a call where we should fit our monolithic and sequential device. Should we go for all monolithic, or should we go for all sequential sort of mechanism? Now, we look into the proposed trade off, what are the basic problem statements, and so on and so forth. Now, look at the left hand side figure, and it shows you a CFET, right? M CFET is basically a monolithic CFET, and a sequential is by S CFET. As you can see, the distance between the top gate and bottom gate, bottom stack, is hardly 35 nanometer in case of a nanosheet FET, right? Whereas for if you do a sequential element, the typical bonding is approximately 60 nanometers between the two, right, or 600 angstrom. Because of this bonding dielectric, because you want the two regions to be separated from each other minimum, because of this bonding dielectric, the structure is taller and has got therefore a larger capacitive loading, which will actually degrade the performance. So, we should also know what is the possible pitfall of this structure. The only possible pitfall is, since it is taller in nature, effective gate oxide or oxide capacitance becomes very like it becomes changes, and therefore, it is difficult to move ahead. However, the structure becomes taller because now you have the sequential element available with it. Let us look at the right hand side figure, which plots L effective versus C effective. C effective is the effective capacitance seen from the source and drain side, and there are two curves which are moving almost parallel to each other. One is basically a A740 mono CFET. A7 basically means 7 nanometer node, angstrom node, and they are trying to do using mono CFET. And once we shift from A7 to 40 to anything which is, say, for A14 5T or A14 5TPS, which are given by the references, various references, right, we see that the A740 sequential CFET gives you a much reduced value of your. So, you see, what we are saying is that there is a decrease in the value of C effective of around 7% when you are moving from mono CFET to sequential CFET. However, the cost you pay for it is a slightly reduced value of your frequency. But and the reason is that, see, so the frequency depends upon the last state scenario. If the last state scenario is such that it is not able to accept the change in the frequency, we cannot be changed to a larger extent. So, what we see is that there is enhancement in the frequency when you go from sequential to monolithic. Mono CFETs have relatively larger frequency of operation. Now, if you, it's quite interesting, I will show you one thing, that if you draw a line here, then it cuts much larger value as compared to this. So, this is approximately 0.96 C effective, right, and this one is C effective is 1.04 is the C effective. And as you can see, therefore, the sequential CFET typically has got higher C effective capacitance, and therefore, its frequency of operation is actually reduced by approximately 6 to 7%. Why C effective is larger? Because your structure is taller, you have effective capacitance being also very large in this case, and that is the reason you see much changed value of your C effective. Similarly, if you plot the graph here, then you see that what we are doing is we are using a sort of 25 nanometer 3 sheet stacks we are taking, right. So 25, so this is the width of the stack, and there are 3 sheets which are available, and inter device dimensions difference is approximately 35 for monolithic CFET, and for sequential CFET the distance between the two stacks is approximately equals to 60 to 70 nanometer, which tells me, and quite an interesting concept here, that surely your sequential CFETs will have typically a larger C effective for the same value of L effective, which my primarily means my F3 dB and F unity gain will be also much smaller as compared to that of the monolithic part. And monolithic is, since it is grown in one by another, there is no flip chip coming into picture. Now let me come to another discussion on monolithic and sequential comparison. The obviously sequential CFETs are more expensive to fabricate than monolithic, and between that and the performance degradation is typically very large. Why it is slightly challenging is, see, it is challenging because when you flip the chip and you try to align it, this alignment has to be exactly same so that you don't allow any overlap capacitance come into picture, which adds to the value of C effective. So how you place that over in this, for example, in this case, how you place, say, let us suppose this part, right, over this part in a proper fashion will determine this value of your problem statement. Now, at this stage, most of the industry prefer monolithic CFETs, and the reasons are well known to us, because it's very relatively easier to go because it's a monolithic process. So you go step by step, and its functionality and its output is much better as compared to a sequential CFET. Now let's look at monolithic. Obviously the cost is low, sequential high cost. If you look at monolithic, there is a low capacitance. Obviously sequential will have high capacitances because of its large dimension, and sequential also has hybrid channel friendly. So you can have multiple types of channel non-silicon, and still the sequential will work fine, monolithic does not. When you talk of integration of two sequential FETs or monolithic FETs, the integration for monolithic is self-aligned fin oblique gate patterning is remaining, that we need to do before we go for a monolithic integration. Then vertical source drain contacts needs to be made very properly. Split gate integration is a challenging one in case of a monolithic one, whereas in sequential one it's basically a 2D integration. As I discussed with you, we will have wafer bounding defects will be there, and aligning the top bottom gate, right, aligning them and obtaining a connection, electrical connection through which you can power up your device is also difficult when you discuss the integration part of it. Now let's look at the middle dielectric isolation. So if you look at the first figure to the left, which is here, right, you do have a silicon germanium sort of barrier which creates a barrier between PFET and NFET. Why do you require this barrier is that, in a sense, you don't want the switching on of either of NMOS or PMOS should affect the status of the other device, and that's the reason you need to grow N-P space. Typically it is shown here as silicon germanium, but you can use an oxide layer in order to isolate these two together. You can also use a middle dielectric isolation, which is shown here in this graph, middle dielectric isolation. So it is what? It is basically a sandwich between silicon and silicon germanium. Silicon germanium is used because of its high mobility. So what you do is that you have this silicon here, right? You have the silicon, and then you have silicon germanium, and then silicon germanium, and then silicon germanium. So there are 4 silicon germanium standard cells which are basically stuck one over the other and gives you a proper value of the output in this case. Now, so this is one structure. The right hand side is basically known as WFM, wafer with patterning, with left hand side no MDI, and the right hand side we have an MDI. MDI is basically middle dielectric isolation. So you can see here, we put an MDI here, this is an MDI. When you put an MDI, you actually are able to separate out the source and drain side very easily, right, and is a well known techniques while using these MCFETs. Now The total resistance, why do you want to find out the total resistance? First of all, is that you want to extract the value of the RC constants, which will determine finally the value of your other parameters related to timing. Now, the total resistance as a function of Lg, which is the gate length for the top gate, and the bottom PMOS is shown on the right hand side. So, as you can see, as the gate length goes on increasing for the fixed value of other activities, the resistance actually goes on increasing, and that is a very well known and no need to explain any further. The reason is very simple: higher the value of L, it becomes more and more difficult for effective value if the gate length goes on increasing, the resistance increases. There are many adverse phenomena coming into picture, but nonetheless, as the length Lg increases, we would expect to see the top PMOS and NPMOS being generated. So, you see obviously, and this is quite interesting, unlike in bulk MOSFET, that the total resistance for the top gate is relatively larger, which is PMOS is larger than NMOS, right. Two reasons for that. Why? Because the total resistance is higher because the mobility of the charge carrier is relatively lower. That is the reason you see a larger sort of a total resistance. Now, what we did was internally, this is taken from a paper itself, and what that paper did was that they took these CFETs and MSFETs and tried to put it into a circuit application, for example, a ring oscillator. And the ring oscillator performance is shown in part A, and part B you can see the parasitics, which is governed by C effective, and this is basically NNP separation. So, if you increase the NNP separation, then the frequency of the operation actually starts to go down, right. So, you do not have a compact device now. If you keep it very further away from each other, chances of having overbearing sort of mechanism will actually lower the threshold voltage of the device, and that is true also, as you can see here, that monolithic has relatively a larger frequency allotted as compared to a sequential one, and it will be easier for us to justify that in our claims. On the right hand side, we have plotted C effective. The author has plotted C effective versus NNP ratio and R reference. So, as the NNP ratio or NNP separation goes on increasing, the effective value of C also goes on increasing. Nothing new in that. This is primarily a basic idea behind the increase in the value of the capacitance. And if you look at R reference versus NNP separation, which is the second slide, right hand side, you will see that if you look at sequential and monolithic, green boxes basically point towards the right hand side, which means that if you are able to make your NNP separation large, you also sort of indirectly ensure that a sequential CFET will be able to stay within the limits sort of, and therefore will gain space in order to generate these limits, right. Let me come to the SRAM layout, and then we will finish this talk. SRAM is basically a 60 transistor layout. As you can see on the right hand side, we have these two blocks available, and this is there, and then we have this cross coupled latch, and then the standard MOS capacitor is there. What happens is that the area scaling with respect to CFET is approximately equals to W effective, and as you can see on the left hand side, the first graph is of FinFET, the second one is for GAF FET, and the third one is a Fox sheet FET, right. And while doing it, you see the GC value, which is basically the separation between the two structure, plays a major role in determining how fast or slow the SRAM cell is working. This is the layout of an SRAM cell, right, where we have the standard lambda based design rules. Using lambda based design rule, standard cell has been designed. We have also worked on nanosheets and CFETs, and we are currently the people are currently working in the domain of memory design using CFET structures. Now, this is the standard layout structure which you see here, right. This is a 4 transistor cell comparison between FinFET, nanosheet and CFET. Now, CFET therefore maximizes the nanosheet channel width by stacking NMOS to PMOS. So, when you go on stacking it, the channel length becomes hidden, and you need to optimize the value of the channel length at any point of time. With this, let me recapitulate what we did till now. We looked into the concept of CFET. How is CFET different from FinFET and gate all around device, and these types are basically your PMOS and NMOS, and how they are integrated in a sense. We also studied the various, I should say, effective capacitance values for effective length of the device, and we saw that in all probability monolithic happens to be relatively better as compared to CFET, right? So with this we will stop this lecture, and when we meet next time we will start with the last part of the CFET. Thank you.